We're seeing that the alternate coordinate systems are turning out to be a blessing with these triple integrals. So for this problem, what we want to do is compute the volume of a solid inside a sphere of radius 9, but exterior to the upper nap of a cone. So these are quadric surfaces that we talked about at the beginning of the class, and so now we're seeing that a problem of this sort works very well with spherical coordinates because of all the circular symmetry. So as in the past, we always juggle with how do we find the phi? That's the most difficult part of the problem. So first, let's look at the intersection. We know that z is the radical here, so when we square it, we just get x squared plus y squared. And so this gives us an equation, in substituting into the sphere equation, we get 2 times x squared plus y squared equal 81, or x squared plus y squared is equal to 81 over 2. Now, in spherical coordinates, then we use this in the last problem, we know that x squared plus y squared is just rho squared sine squared. And so, if you will, we just set that equal to 81 over 2, noting that the radius of the sphere is 9. So 9 squared is what we put in for rho squared, and of course the 9 squared and the 81 absorb, and we have sine squared phi is equal to 1/2. Now, of course, by the square root principle, sine phi is plus or minus 1 over root 2, but our values for phi lie between 0 and pi, so we select the positive, and of course the inverse sine of 1 over root 2 is pi over 4. So now we see that the cone actually intersects at an angle of pi over 4, and then we just have to move all the way up to pi over 2 to cover the volume exterior to the cone. So of course, theta will run from 0 to 2 pi. Now we know that phi runs from pi over 4 to pi over 2, and of course, rho runs from 0 to 9. So all of those limits are constants, and so that's going to make for a very simple integral as long as we stay with the spherical coordinates. You can see that our coordinate systems are very useful. So by definition, the volume, if I call this region here Q, the volume is just the triple integral of the volume element over Q. And we have described Q, as we've said, in spherical coordinates. So we have the integral from 0 to 2 pi, pi over 4 to pi over 2, and 0 to 9. And of course, the dv in the spherical coordinates is rho squared sine phi, d rho, d phi, d theta. And of course, we can separate out all of these integrals because of the fact that all of our limits of integration are constant. So we get the d theta integral from 0 to 2 pi, we get the d phi integral from pi over 4 to pi over 2, and we get the d rho integral from 0 to 9. Of course, the first integral is just 2 pi, and then of course the antiderivative of sine is the negative cosine, evaluated from pi over 2 to pi over 4, and then of course add 1 divided by the new power, we get 1/3 rho cubed, evaluated between 9 and 0. And of course here the cosine of the pi over 2 is 0, so we're just left in this case with 0 minus 1 over root 2, as cosine of pi over 4 is 1 over root 2. And then of course with this negative here, we just factor it to get negative 2 pi. And then of course here, we cube 9, I just wrote it as 81 over 9 so we can easily absorb the 3. And so now the negatives absorb, and the root 2 will absorb into the 2 to give us a root 2, so we have root 2 pi. And then of course 3 absorbs into the 9 to give us a 3. 3 times 81 is 243. So the volume that we're looking for is 243 pi times the square root of 2. And we are done.